First, I'd like to thank the organizers very much for inviting me to this very nice and interesting conference. So here is the outline of my talk. It's very simple. I want to explain this set of pictures and that one. And so here is the motivation. So what I'm interested in is basically the Brownian map or a random map, and now we understand the metric structure to some extent, but the next step is to understand its conformal structure or reliable quantum gravity. And so in general you could ask, given a two-dimensional surface, how should you parameterize it in a most natural way? So if it's two-dimensional, it usually means it's homomorphic to, for instance, to the sphere. Okay, so if you have a smooth surface, then the conformal map, the angle preserving, so it's a diffeomorphism. So if it's smooth, there is a diffeomorphism, and then the one that sends, say, in the plane the rectilinear coordinates to a right coordinate system. That is a preferred one. Gauss already studied that, finding isothermal coordinates. But sometimes, like in this picture here with this annulus, there is some obstruction. So in the presence of moduli, if you have an annulus of thickness 2 and another one of ratio 4, there is no conformal map. Then you can ask for the map that is the least non-conformal. Which one is closest to conformal? And that one is called quasi-conformal. There's a very rich theory, which is the foundation of Teichmüller theory. So you can ask questions like that. Which are those sort of most conformal maps? Now on this slide, I want to show some surface which I think is a very nice toy model for quantum gravity. At least it helps me to understand beautiful theorems of Jean-François and the confluence of geodesics. So take the cube, the unit cube, and then here you see only the top face subdivided 3 by 3, and on the middle just place a smaller cube. And then with each of these smaller faces that you see from the 9 by 9 subdivision, you still subdivide 3 by 3, and in the middle put a smaller cube. And you keep continuing. So that's a three-dimensional version of the two-dimensional Van Gogh snowflake. And in the end, you get a surface that is sometimes called the Manhattan surface or the snowball. And my former student, Daniel Meyer, basically following an idea of Rick Kenyon's, proved that there is a very nice parameterization from the plane onto this wrinkled surface. There is a parameterization that has this property of quasi-conformality. Basically, I don't want to give rigorous definitions, but it says that this map will be very non-smooth because the surface has no smooth curves on it. But it has the edges, but very few smooth curves on it. But it's still this parameterization has a property that if you have 3 points of roughly the same distance with each other, then on the image side, the 3 distances are still roughly the same. So relative distances will be distorted only by bounded amount. So that's one of the basic properties of conformal maps in smooth settings, and it's a defining property of quasi-symmetric maps in general metric spaces. So the construction goes roughly like this. You just take a finite approximation, like here the first step where we didn't have the blue little squares, and you realize that as a Riemann surface by gluing Euclidean unit squares. You just glue squares together. Yes?
Yeah, you mentioned the property of confluence of geodesics. So is this property?
Well, on this surface here, if you cut this surface sort of right in the middle, what you see is a Van Gogh snowflake, something non-rectifiable. But if you want to go from the very top to the very bottom, you would not go along the snowflake. You just find these highways in some sense, these edges, and then that way you can actually see that between any pair of points there is a curve whose length is comparable to the distance. Yeah? So the sort of path, it's a path metric actually. And so, but the way you travel is not in the obvious way, but you really travel by finding fast way. This is nothing that is written down and that I have even checked carefully. It's just, it seems to have that feature. But okay, so how do you give this a nice parameterization? Just take a finite approximation, do finitely many squares, and then view that as a Riemann surface. And then it is actually, in this case, it is not so hard to find explicitly, compute explicitly this uniformizing map. And so here is just to indicate on the next level generation that you see, this one here would be one of the squares, but it goes all the way down here. And then it's subdivided into the smaller squares. The middle one, the cube, and then the middle is subdivided further. And this is really what you would get if you take this Riemann surface that you see up here, uniformize it, and pull it back to the plane. So now you can take the first approximation, the second one, higher approximation, you get a sequence of maps, and you can wonder about convergence. And this is what Daniel proved, but it's, again, Rick Kenyon with his co-authors, and in a different work, also Mario and Bruce. So these give methods how one can actually prove that the limiting map exists and has this required niceness. Okay, so that is a deterministic setting, but I'm interested in the random setting, and I very briefly review. This is just for motivation. If you've never seen the Sheffer bijection, you probably won't understand it from the 1 minute run-through that I'm giving. But you start with a planar map, in this case a quadrangulation, and it's rooted as usual, so here's the root. Then you compute the distances from the root, 1, 1, 1, these are 2, 2, 2, 3. And then in each of these faces, in each of these quadrangles, you introduce an edge based on some local rule. So from the labels of a face, you decide, I won't describe this rule, which edge to put. And then you remove the original edges of your graph. What is remaining are these new red edges that you introduced. And then one can prove that with this local rule, this is a tree. So the upshot is, as you've all, this is smiling, this is a brilliant, beautiful bijection between trees that are still having this label around and the original quadrangulation. So I just want to use this as basically to explain why we care about trees and why we want to glue trees together. So there is this important Sheffer bijection and this beautiful work of Jean-François Ledal and independently Gregory Memoir, proving basically that the scaling limit of these quadrangulations with n faces, if we scale distance, graph distance by n to the 1/4. So now we take a quadrangulation with n faces, we scale graph distance by the 4th root of n, and this metric space converges to an important space called the Brownian map. Convergence is a Gromov-Hausdorff distance. This is a deep theorem, and if you have never seen it, then I'm sorry you won't be able to follow this, but because it's an important theorem, you've all seen it, I assume. And so what is this based on? The proof of this is actually based on a concrete description of this limiting space X, which comes out of the Sheffer bijection. So you have this tree here. Now when n goes to infinity, number of edges go to infinity, and this tree, being a random tree, converges to a continuum random tree. And the labels are like a random walk along these branches. They converge to Brownian motion, so along this tree. And this whole object of the limit is known as a Brownian map. Now, there's another nice result by Jean-François and Proudhon, saying that this limiting object, this Brownian map, is topologically a sphere. So this construction here basically says, well, it can be reversed. So we can, from this labeled tree, it's a bijection, we get our map back. And so the sphere, this Brownian sphere is, wow, this one is getting, losing its power. So there's a first tree, the CRT, and then there's another tree that can be viewed as coming from these labels. And when you take the union of these two trees and then the equivalence relation under, well, what you see in this picture, you're putting back the black edges, that gives you the sphere. But this is a construction that only works on a level of metric spaces. There's a different construction due to, I think this is Mullen bijection, which then was sort of improved by Scott Sheffield, and then there is this work by Bertrand, Jason Miller, and Scott Sheffield, that also gives a bijection between a pair of trees, so a disjoint union of trees, and some equivalence relation. This is this hamburger cheeseburger construction, and out comes the sphere. And again, that's a metric space and doesn't have its conformal structure. But it suggests that, it suggests that if we want to look at a complex structure on the Brownian map, we would like to look at trees and like to glue them together conformally. So now a lot of my work has been influenced by deterministic results. And in the deterministic world, this is actually a well-known object, how to glue two trees together to form a sphere. So in the complex dynamics world, that was actually done here in Orsay, I think, he invented that notion of conformal mating. So abstractly speaking, there are trees here. You should best think of a Julia set, like this black tree here. There's a dendrite embedded in the plane, and then you have a second dendrite, and then you take this joint union, and you define a certain equivalence relation that I will sort of indicate later. But it's best explained that equivalence relation comes out of this. When you have this dendrite in the plane, you can take, it's connected, and you can take the conformal map from the outside of the circle. So you take the exterior of the disk, conformally map it to the exterior of this dendrite. And then, okay, so what is then important is this picture here tells you, for instance, many points here, they have two approaches, one from this side and one from that side. So one point on this side has two pre-images, and what this picture here tells you inside the disk, which are the points that are glued together. This is like a triangulation, infinite triangulation of the disk, called a lamination. And what the conformal map is doing, it contracts all these chords inside the disk. For instance, this whole triangle here, this white triangle will be contracted and becomes this one triple point where the dendrite branches off. And so now how do you glue two trees? So in order to define this precisely, that's kind of difficult, but I'll just show a little movie. That movie was made by Arnaud Chéritain, and it shows a little bit how this conformal mating works. So initially you start with two trees, like the one on the right and on the left, and you think of the right one, say, independently of the left one. Now you take an equipotential loop around it, and think of the potential as being, well, first if it is large, then the equipotential would be almost like a big circle, and as the potential gets smaller and smaller, the loop around it will get closer and closer. So you take a equipotential on both sides, and you glue these two equipotential curves together. These potential curves, they would have a parametrization that comes from this conformal map here. So the angle that you see here gets transported over here. And as it contracted, what you'll find is, so these equipotential curves that are now glued to each other, as the potential gets smaller and smaller, they have to hug both curves at the same time. And so here you should imagine the equipotential curve as being a loop that goes around this one. And so here you still carry the conformal structure of the original dendrites. And you see as the potential gets smaller and smaller, you can sort of almost see already the piano curve that forms in between them. And maybe I should stop here, because then you stop seeing things. And those of you who know Scott Sheffield's work on the Liouville quantum gravity will recognize that this picture looks very, very close to actually the quantum gravity measure that you see there. So I shouldn't say much more there, but if you took the parametrization of this equipotential curve by angle here, so uniformly distributed angle, that density would be not uniform anymore on that side, and this is basically the measure that you would expect to see in the limit. That's very similar, I think, to what you expect in quantum gravity. Okay, so that's how we glue deterministic trees. And I would like to advertise another theorem of my former student Daniel Meyer, partly because Daniel is on the job market again. He was at the International University Bremen, but they have financial problems and had to release the youngest member. Anyway, here's a beautiful paper of his that says that often this process can be reversed. So rather than gluing two trees to form a sphere, in many situations you can take a sphere with some extra structure known to the experts as post-critically finite rational maps, and you can find the two trees in it and the piano curve that sort of is wrapping around these two. So that didn't make much sense if you have never seen that before, but so I should like to say this is well understood. It's difficult but well understood in the deterministic world. And if we try to implement this now on the random side for the Brownian maps, then first we have to find these trees. Right? Before we can do two trees, we have to have one. So this is the question that I would like to discuss a little bit. It was posed or communicated to me by Jean-François Legal pretty much exactly 5 years ago at the conference in Switzerland. And so if we start with a Brownian lamination, so think of this as the disk, and you take a triangulation of the disk, uniformly chosen at random, when there is, let's say you have n equidistributed points on the circle, n very, very large, and you take a uniform triangulation. And the limit the Brownian excursion with the usual coding. And now we try to find a conformal map that actually pulls each of these chords down to one point. So it should be a map that is angle preserving outside the disk, but inside the disk, the whole disk should be squished and form one tree. And the question is, does such an object exist? And so what I would like to, obviously it does exist because there's a picture of it. And so now I would like to explain, first of all, how to compute this, how this picture was made, and then what do we know about this, this question and related questions. Is there any questions? Okay, so we take the Brownian lamination of the disk, a large random triangulation, and try to find a conformal map. So I should like to say already for very small trees, you don't have to take like this one, maybe 1,000,000 points. If you take already very small triangulation, it's already a very interesting problem. And here is a theorem that is hard to attribute to anybody in particular, but these things are called Shabbat polynomials, and so I think Shabbat was probably one of the first. I learned this approach from a paper of Bian, and Chris Bishop had a recent paper. And so this, it says the following: if you're given a finite tree, every finite tree can be drawn on the plane in such a way, like here, that every edge has the same harmonic measure. So if you start a Brownian motion at infinity and you walk around until you hit the set, then each edge has the same hitting probability, 1/n if there's n edges. But moreover, each small segment on each of these edges has a probability to be hit from the top and from the bottom, and both harmonic measures coincide. It's perfectly balanced. It's what Bishop calls a balanced tree. So in the symmetric case right here, it's obvious. You just draw a star with equal angles. Here it's already, most of you know that hitting probability near the tip is higher than in the middle, so that's why the edges have to be sort of shorter to the Euclidean eye. And you know, these edges will not always be straight. Here you see already that they're slightly bent. And there are many ways to compute those. These are actually Grothendieck-Descend's fonts. It's a special case of that. You can view the problem of computing them as just a question of, you could say, well, what we really see here is a triangulation of the sphere where you introduce one vertex at infinity and you join that vertex to all these existing vertices to get a triangulation of the sphere. You think about gluing triangles together, and that's how you can realize that there are many non-trivial equivalent ways of thinking about these objects. But for us, the easiest one to actually deal with the problem of computing these is to say, well, once you have the tree, just take the conformal map from the outside of a disk to the outside of this tree. And then because the harmonic measure of each edge is the same, you will find the two nth roots of unity. If there's n edges, you will have two n sides to it, and so these will be the two nth roots of unity. And then they have to be glued here according to the pattern that is, you know, given by the tree. So you have a conformal welding problem starting with the outside of the disk. The inside has to be sort of glued together in order to form this tree. And that's it. So in the finite case, it's not hard to see that this problem has a solution. And so what we've done with Don Marshall is to actually implement it, write a program that actually does it numerically. And this is already interesting to do numerical experiments with it. For instance, I was a bit surprised to see this picture of the binary tree. There's 11 generations here. And what you see, so each of these little branches have the same harmonic measure. And the question that Brent asked was, is actually every edge now, the ones in the center, do they stay macroscopic or will they become microscopic? And so here you can see already lurking in the background that when n goes to infinity, here n is 11, you will see a sort of limiting curve that has some interesting behavior, some sort of cusps here. But anyway, that would be the deterministic picture. And we are more interested in the random one, so I'll come to that in a moment. But very briefly, what is the zipper algorithm? How does it work? Maybe I'll show that in one picture here. So suppose we wanted to find this tree here based on this lamination of the disk. Then we do it one step at a time. So we'll find sort, in some sense, this edge first. We just glue these two edges together, not worrying about the rest of the disk. So we take a conformal map from the outside of this disk to the outside of this disk that just zips up these two end intervals. And that one you can write down explicitly. That's an easy sort of first-year graduate problem. And then you zip up the next pair, and then this pair, and then that one. You zip them up one pair at a time. So. And surprisingly, there is something more to it, but the surprising thing is that this actually works extremely well. This works with an enormous accuracy. So I should just not say too much about it, but for instance, here we made a sort of catalog of all trees with 5 edges, and here with 7 edges. These are all trees computed. And okay, so I don't want to say too much about it, but the computation of these is actually of huge interest in some areas of mathematics, computation, algebra, and algebraic geometry, and number theory. And people made a catalog relatively recently of all trees with 9 edges. And there was said in this paper by Kuchekov that trees with 10 edges, you make a catalog, is difficult work, probably nobody is going to do it in the foreseeable future. But then with our program, we made a catalog of degree 14 edges, which is about 100,000. And of course, the difference is when you do it by hand, you have to compute many things. In particular, there is a number field that is of interest to compute. Whereas our automated thing can compute, say, 10,000 digits. We can get the roots up to an arbitrary precision. And from there, you can then use lattice reduction algorithms to actually compute the fields.
So is this way of drawing trees unique up to?
Yes, that's a very good question, but that's a nice simple exercise. There is one and only way up to rotation, dilation, and translation. It's a unique way of drawing trees. So there's a huge industry. I mean, there's about 1,000 papers about this field of mathematics that I don't want to. Because we are not interested in degree 14 trees, we are interested in a million. I mean, we're interested in the limit. So the limit, well, what do we know? And in the limit, because it's hard to compute the small ones, so what do we know about the infinite ones? One is this nice paper by Chris Bishop with the title Trees Are Dense, where he proves that every compact subset in the plane with obvious sort of caveats can be approximated by such trees. But of course, you have to work very hard. If you give me a favorite, I mean, for instance, it has to be connected and has to have no interior. Well, now let's. Basically, every connected compact set appears in this catalog if you look at it with a Hausdorff distance I. But of course, you have to work hard to find the precise tree in your catalog, and that will not be the random typical behavior. So how does the typical tree look like? And this is a theorem with my former student Joel Barnes, that at least subsequential limits do exist in the topology of conformal maps. So if you look at the conformal map to the outside, then there is a distributional limit, so n would be the degree, and you want to say Fn, the sequence converges distributionally to a conformal limit. This we cannot prove yet, but at least we know that there's non-trivial limit, so there is something interesting out there. If you think of the star, when you have a star with n edges, n is very large. From the outside, you can't distinguish that star from a disk. So that would be the case where the limiting map is the identity. But so
this is for an infinite tree or for a sequence of finite?
Okay, this is a distribution. So think of if you have n trees. So you have the probability measure on the space of all compact sets. So you have Dirac mass at each of these trees. It's in the usual way. So this is the measure on the space of compact sets, p sub n, and that converges to some subsequential limit, p, and that subsequential limit, p, is non-trivial. But in other words, I mean, intuitively, if you take a random, you open that catalog at a random, n is huge, you open it on a random page, you look at this thing, what you see is not round. It will be a dendroid-like object. This is not the right theorem, because what you really want to prove is that the picture you saw before is the right thing. But again, going back to the deterministic world, it's already hard enough to understand what laminations of the disk in the deterministic world give you nice trees. So starting on this side, can you rebuild the tree? That's the true question. And all I want to say here is there is now a theorem that basically tells you exactly what is the right condition on the lamination in the deterministic setting to give you what's considered a nice tree, one where each of these branches are quasi-conformal arcs, so they don't have bottlenecks. So that's exactly the analog. In tight Miller theory, you have these quasi-conformal arcs, and then it's well understood what conformal welding gives you quasi-conformal arcs, and that's the analog. I would say it's a good step towards understanding the random lamination, but there's still a little bit of work left to do. Which after 5 years, well, I don't know, maybe I feel I'm pretty close, but I felt that before, so hopefully next year I know how to prove that same theorem for the Brownian lamination. Okay, so here is just basically to show that the theorem exists. The condition is slightly complicated, so I will skip over it. But okay, so the goal here is to prove that if I replace such a deterministic lamination by the Brownian lamination, then there really is the conformal map. There is a conformal map that solves this problem of zipping up all these chords. And the tree that you will find here is the tree that I showed before. Numerically, we can see it, but it's still not proved to exist. So at the point, this is where this project is. That's the state of that. And I would like to now come back to the original motivation here, to the snowball. Because the one approach was to try to glue these trees, and I don't know if this is ever going to work. But there is another interesting feature that I want to mention. And it is this: if we take the surface here and we intersect it with a plane, with any plane, but let's say the one that is defined by one face of the original cube, what we'll find actually is a Pinsky carpet here, right? This in the middle, this is where we erected the next little cube, and then the cubes of second generation. So the intersection of the snowball with the plane is just a Pinsky carpet. And you could try to understand the surface by understanding these levels. It's like a level set of the height function. If height is just the z coordinate. And in a similar fashion, if you take the random surface like the Brownian map, you find the conformal loop ensemble, CLE, inside it. I mean, usually it's defined on the discrete side, and we heard it talk about the Potts model. If you had a random map, you can still define a Potts model on it, or an FK clusters, and it's believed that in the limit, as n, the number of phases go to infinity, that these will converge to CLEs on top of the random map. So then, understanding this limiting object, one question you can ask yourself: if these carpets, these CLEs, if they have some sort of conformal structure. So here you see a picture that was made by David Wilson. That's an easing, sort of easing configuration in a disk. And according to David, Rick proposed to look at a sort of a uniformization, a circle packing of that. You look skeptical. David said that was your question. And so anyway, so I'll explain now what this picture is. How can we make the easing carpet CLE3? How can we make this one round? And so to explain that, let me very briefly say a word again about the deterministic setting. So we all know the Riemann mapping theorem. If we have a simply connected domain, there's a essentially unique conformal map to the round disk. So if there's no holes, then on the image side we can pick the disk. If there are some holes, but only finitely many, then a theorem, classical theorem of Kuiper, says that still there is a conformal map. I can make each of these boundary components round circles. Now there's fewer degrees of freedom, but still I can map this multiply connected domain to a circle domain. So now you can ask yourself, how about if there are infinitely many holes, like in this Pinsky carpet, can I make all of them round at once? And you immediately wonder, wait a second, now what's left here is the black set. The black set has no interior point anymore. So if it hasn't any interior point, what does it even mean to be conformal? Differentiability is not a reasonable question. And yet, if you remember what I said earlier, there's this notion of quasi-conformality or quasi-symmetry that makes sense in every metric space. And the somewhat surprising fact here is a beautiful theorem of Mario Bong's, and then with his collaborators to give it the final touch, which says, yes, indeed, there is essentially a unique round carpet associated with such a deterministic carpet. So the precise statement would be this: if C is a nice carpet, it doesn't sound very precise, but it can be really precise. So if C is a nice carpet, then there is an essentially unique, after Möbius transformation, round carpet and a nice homeomorphism between these two carpets. So the amazing thing also is, first of all, the existence, but also the uniqueness of this round carpet. And nice means on the pre-image, the first nice means that all these holes here, all these loops, are quasi-conformal circles. So they are curves that can be Van Gogh snowflakes or so, but they don't have sort of zero-angle cusps. And one more property, that the distance, relative distance, two loops never come too close to each other. So the smaller the loops determines basically the distance of those. The distance between two loops is at least as large as the size of the smaller of the two loops. And nice homeomorphism means just quasi-symmetric. Again, relative distances are distorted only by a bounded amount. So that is the theorem in the deterministic setting. And so what Brent, Vernessa, and I were trying to do is to see if this or such a theorem could perhaps still be true for the
carpet is such that every component is a...
Yes, so what is a carpet? That's a carpet is just a collection of disjoint loops. So there is no nestedness here. It's disjoint Jordan curves.
No, that's fine. That every component is a circle?
So on this one, on the round carpet, yes, every component is a round circle. Yes. One assumption for the uniqueness that one needs, for uniqueness you need that the original area, the black area is measure 0, and then the round circle is actually unique. If the black area is positive, then it's actually not.
And is it really obtained by approximating?
Yes, so the proof actually is surprisingly naive in a sense that, so everybody here knows the Ising model, so I don't have to say much. There's we have these three phases, high temperature, no correlation, low temperature, and then there's the critical phase where we have the critical temperature where we have these interphases. So let's skip that one. And yes, so the proof is exactly as you suggest, in some sense it is. You take one loop at a time, you make them round, you apply Köber theorem, and you pass through a limit. So let me say, before I state that, I at least want to remind you, so again, this is the picture of the Ising configuration. You see this very light gray is sort of, well, you see three shades of gray. In here, the dark gray one, these are the nested loops. So we ignore the nestedness. We only take one level, only these outer loops. And then I'll show in another picture what exactly happened here. But intuitively, the way you should understand it is the light gray is the carpet. It's a complement of these darker gray loops. And then there is a correspondence between this carpet and the round carpet. So, and unfortunately, this picture, just 1 second, it has to be rotated a little bit. So the picture has to be, if you take the circular one, rotate it by 45 degrees, and then also flip it over. So then that's a test on your image. So these two guys here, these two gray loops are the two top ones here. And these three big ones are these three big ones. So you see, rotate this one 45 degrees and flip it over. And then you see the ones down here, over here. So there was another question.
Is this an Ising configuration at criticality?
Exactly. This is this is at criticality. Yes. And this is the CLE4, so you could think of these as level curves of the Gaussian free field, for instance. And so the theorem that so here is a zoom in of this Ising at criticality. This is done on a hexagonal lattice. And then maybe I should say, of course, David did not compute a conformal map from this very highly connected region to a circle domain. What he did, he just invoked the circle packing theorem. So here you see it at work for triply connected domain. If you just have three boundary components, the outer one and two of these loops, you fill up the rest with the hexagonal pattern, and to get this simplicial approximation here. And then you introduce one vertex for each face, one for the outer one for these two inner ones, to get this graph. And now circle packing theorem tells you, now you have a triangulation of the sphere, so you can circle pack it, one circle for the outer face, and for each of these bigger loops, for each of these vertices, now you have a bigger circle. And it's known that when the mesh size here goes to 0, that this will actually converge to the conformal map. But there is, of course, two limits here, because you have infinitely many loops and the mesh is given, so it's not clear what this really means. That's why this is only an approximation. So when you zoom in, you see all the original small circles corresponding to the original hexagonal grid, and the bigger the Ising sort of loops. So anyway, I think already the pictures that David made are very impressive and very interesting. And so the theorem that Brenda and I proved, we don't quite yet have Mario Bonk's deterministic result. We cannot prove convergence, but we can prove subsequential convergence at this point. So we can prove the following. If you, maybe I should write out what this setup is, exactly as Asaf, as you said. Take finitely many, the first n loops. You have two singled out anyway. The one that you want to make the outer one, and one that you want to normalize as the inner one. And these two normalized loops, they're used to sort of define, let's say, the unit circle and the circle centered at 0. And then the other loops are labeled 1, 2, 3, and so on. And you take the first n of those, and take Fn, the conformal map from this n-connected domain to a circle domain, given by Köber's theorem. And now you want to let n go to infinity, and you need to show that this picture, this is not degenerating. So basically what the theorem really says is that with probability 1 for any pair of these loops, the ratio here is bounded above and below. Then it's very easy to prove compactness. So what it really boils down to is to show in some sort of conformal, to define a distance between these two loops and show that this distance stays bounded away from 0 and infinity independently of how many loops you throw in there. And then you want to show on top of it, this is not exactly how Mario approached it, but this is what works in the CLE setting. And so, so that's the statement. You take finitely many of your loops, you throw in one at a time, and the aspect ratio never degenerates. Okay, so here are the ingredients of the proof. I won't say much about the details, don't worry about it. But the first one is it very heavily relies on the construction of CLE. There are many definitions to define CLE, and the one that is most used here is the one of Scott Sheffield and Wendell and Werner's, based on the Brownian loop soup and the Poisson point process and clusters. So this one I will not, that would be an interesting long talk in its own, so I won't say anything about that, but that's a sort of working definition of CLE. Then I want to say a little bit about the next step, that's Schramm's transboundary extremal length, because that's a very interesting notion as well. So here the idea is we need to measure the distances between a pair of loops, and what is the right way to approach that question, how to measure loops, especially when there's infinitely many obstacles in the middle. And then the last part is work. So let me very briefly at least mention what is this, that's a transboundary extremal length. So our situation is we have these two loops to begin with, and then a large number of loops between these two. And we should think of this original configuration as a cylinder of a certain height h. And if there were not these loops in the middle, we know how to compute this, this height. Maybe it's best to think of an electric network here, and then you just take the effective resistance between these two loops. And so now, so one way to approach this effective resistance is by such an L2 minimizing problem. You look at a metric, a conformal metric in this annulus, and you look at all conformal metrics, rho, that give length 1 at least to every curve that goes from here to here. So here it's clear, every curve here has length h or more. So here the problem you set up is to give every curve length 1 that goes from here to here. And then you minimize just the L2 mass of such a surface. Okay, but in the presence of holes, now a curve that goes from here to here, or a connection, could take shortcuts through these loops. And how should you control these loops? So in the electric network analogy, the way you should think of it is you don't want to cut out this loop, but in a sense you want to contract this whole loop to one point. That's not exactly what you do, but that's in some sense you compute the effective resistance from top to bottom, where each of these loops counts as one step. So again, you take a metric on the remaining annulus here, given by a function rho living on the complement of these loops. But now each of these loops gets a weight, call it rho sub j. It's just some number. And now you want to still look at all curves from top to bottom, and the length of such a curve is given by integrating the density over the continuous part and you pick up the weight rho j for each hole that you go through. And so you want to take admissible metrics where the length of such a curve is at least 1, and then you minimize again their L2 area. So that's this what's called transboundary extremal length, and this is the reciprocal. So you take 1 over this minimum, or 2 pi over that minimum. That gives you then the height of another cylinder. And the interesting feature is that actually this minimize is achieved by taking squares out of a cylinder. So there is a round cylinder with square holes in it, a conformal map from here to here, and each loop is mapped to its corresponding square. And the size of these squares is basically determined. There's no freedom here, it's only a rotational freedom. So there's a unique set of weights, which is the size of these loops. So by means of this transboundary extremal length, you can make every loop a square. We want disks, but squares are not so bad to begin with. So now the thing is degeneracy. First, you need to show that these guys don't degenerate, and there's a simple lemma. It's basically an exercise in Cauchy-Schwarz that says that the ratio of these heights is bounded. So h prime over h is bounded by essentially the sum of the square of the width. So each loop sits in a sort of rectangle of a width w and height h. If you sum up the square of the width versus the sum of the square of the heights, if these guys are bounded, then the ratio is bounded. So that's the sort of main tool that we're using. And as a corollary, if the sum of the diameter squared here is bounded, then clearly the sum of the width squared and height squared is bounded, then the ratio is bounded. And so the theorem that we end up proving is that the sum of the diameter squared of these loops is finite almost surely. So once you have, that's sort of where the hard work comes in. And I'm starting to get over time, so I should stop at this point. So this is only the first step, existence of subsequential limits, and then there is, after this is done, there is so many more things. So uniqueness, for instance, will need one new idea. At this point, I should stop. Thank you very much.
So we have time for questions.
Yes. When you show this theorem that states that basically any compact subsets with some properties can be represented by a tree, is this representation, it cannot be unique, or is there some unicity or something?
It's very highly non-unique. It's just it's not unique at all. And the degree will have to be excessively large. If you give me your favorite drawing, so it has to be a compact set and it has to be connected, and that's basically it. And then the tree, the degree, I don't know. There's probably no a priori estimate, but it will have to be insanely large.
Yes.
And again, so the majority of the trees. So if you made the catalog of all the trees of the degree you need here, it would be almost all of them will actually be dendrites, like the picture I showed, a little bit like this Julia said dendrites. So they will not do what your favorite picture is doing, forming big loops or so, or like we draw a dog with a tail, just keeping it connected. So that's not how it's going to look like. But, if you wait long enough, it's like in probability 2. I mean, whatever happens will happen eventually, which is with insanely small probability.
Yes, but is there some notion of entropy or associated to this?
That's a good question. I mean, we know so little about it.
Is there a conjectural measure for what the tree, the limiting object?
That's a good question. I don't have a conjecture yet.
Yeah.
I'm almost certain I'm willing to bet.
Let me ask the question again now that I have the microphone. Is there a conjectural measure on compact trees, dendrites, that arises from your random triangulation?
Yes, and in some sense it's not obvious, but these quadratic Julia sets, they have this nice symmetry. You take this Julia set and it really has this point of similarity. 2 copies of it give you the same Julia set. And here it's the same thing. So there's this law on dendrites. I mean, this is a speculation, but I'm certain that it is true. So there's a measure on the space of dendrites. These things will be dendrites. And they will have the property that the conformal map from the outside of the disk behave like SLEs. It will be Hilbert continuity. So they will have house of dimension bounded away from 2, almost surely constant. And now, just the law of the CRT. 3 CRTs together give you 1 CRT again, right? I mean, with the right interpretation, you have to adjust the size according to the Dirichlet distribution. Same here. You have to take 3 of these dendrites, and then you take, according to the harmonic measure, uniform chosen points, and you glue them together at this one point. Out comes the same law. So it has this very strong self-similarity property. You just have to state what does exactly gluing mean. How do you glue these embedded trees? And that's by means of the conformal method. I mean, you have to glue their eliminations. That's as I can say. I mean, that will characterize them. And it's almost obvious modular existence of the, the question is the usual question of local connectivity, the one that is bugging, local connectivity of Mandelbrot said it's always, given conformal maps, they don't exist on the boundary a priori. And so here, this is the technical problem. Just with SLE being a curve, it's always the same problem. Apart from that everything's
Okay, I think we can continue. So let's thank Steffen again.